Peroxide, do you have a phone charger with you?
Sure thing.
This one won't work with my phone. Do you have another one? Check the port.
I have the ideal one for you.
What is this? How does this thing work? Bhanuka, how does this thing work?
Let me see it. This is a mobile phone battery charger. But the thing is, you have to take the battery out from the phone.
Is that so? I cannot take my battery out of the phone right now. Anyways, guys, thank you very much. You guys carry on.
This is a good idea for our reverse engineering project. Let's take it to the lab.
Okay, let's take the lab.
This is a universal lithium-ion mobile battery charger. It can operate in 110 to 240 volts, and you can charge batteries ranging from 2.8 to 8.7 volts. So it's very useful when it comes to situations like if you have lost your mobile phone original charger.
So let's try to disassemble this charger. It is very easy. It has only one screw, so we can easily remove it.
We have taken out the PCB of the circuit. Let us now identify its components. First, we can identify a high-speed switching transistor, and this is a high-frequency ferrite core transformer. So this sub-circuit might be a switch mode power supply. This is a LM358 op-amp IC. There are three LED indicators in this circuit. First one is to check whether the power is on, and second is a blinking LED to indicate charging. Third one lights up when fully charged. So let us now trace the PCB design of the circuit. 1.
Now let us trace the PCB design. We have finished tracing the circuit. Now we are going to draw this again using multisim.
So far we have identified all the components of the circuit, and we drew it in the multisim software and simulated some parts of the circuit. So let's analyze the circuit first. We can see that this lithium-ion battery charger has a switch mode power supply. In here we can see a high voltage high speed switching transistor. The main advantage of the switch mode power supply is the greater efficiency because the switching transistor dissipates little power when acting as a switch, and also a lower heat generation due to high frequencies. And so SMPS is the best solution for this kind of smaller device because the heavy line transformers can be eliminated. But when the efficiency goes high, the complexity of the circuit also goes high. The first stage of the SMPS is to convert the AC signal to DC signal. But this signal is an unregulated DC signal. This signal is then fed into the switching transistor. This switching transistor switches on and off at high frequencies. And these output pulses are then fed into the primary of the transformer. So this kind of high frequency transformers are optimized to create the smallest possible size, and it overcomes effects like eddy current losses and leakage inductance, interwinding coupling capacitance. So the charging part of the circuit is done without a dedicated IC. All the output indicators are done via the 2 op amps here in this LM358 IC. So in this op amp configuration here, work as an oscillator, and whenever the battery is charging, this op amp produces a pulse-like wave and this blue LED blinks. And this op amp configuration in the right side works as a voltage comparator. When the main supply is switched on, this red LED turns on. So these are the 2 terminals which is connected to the battery, and you can see that here is a feedback path from the battery to the comparator. So it continuously checks with the voltage of the battery and compare it with the reference value. If the battery is fully charged, there comes an output to this LED. We have successfully finished our reverse engineering project.
So that's the end of our video.
Thank you for watching.